So yesterday we started talking about centripetal force. So let's apply this in a couple different ways, and we'll do this with driving a car, because either you guys are driving or you'll be doing so very shortly. So let's take a couple examples of a banked and an unbanked curve. So when you're driving your car around, we'll take the unbanked curve first. It's a little simpler. So around a curve where it's just flat. Okay, so it's a flat piece of road, but you're just going to turn. Okay, so let's just come up with a problem here. So let's say there's a car rounding this flat unbanked curve, radius r, and there's a coefficient of friction, it would be static friction between the tires and the road, it's mu. So what's the maximum speed at which the driver can take the turn without sliding? So the first thing I want to do is draw a Freebody diagram. So I'll draw a Freebody diagram as it's right there. So I've got weight, pulls it straight down. I've got a normal force that's perpendicular to the surface. And I've got a frictional force. Now the frictional force is what provides the centripetal force. Okay, so these are the only forces acting on the car here. So just like before, I'm going to write a second law equation for the x and y directions. So just like always, I've got F net equals ma in the x and F net equals ma in the y. So let's do the y first. That's the easier of the two. So in the y direction, I'm not accelerating. Okay, so there's only two forces, so I have normal going straight up, and I have mg going straight down, and they both equal acceleration, which is 0. So normal minus mg equals 0, so I can just say Fn equals mg. I'll leave it at that for now, and I'll swing it over to the x direction. So this is where it gets a little interesting. So because this is moving in a circle, my acceleration is a centripetal acceleration. So my net force, F net in the x, is equal to mv squared over r. So remember what we said yesterday, we have our centripetal acceleration is just v squared over r. And I just make that substitution into here for this a. So now I have F net equals mv squared over r. So what are those forces? The only force in my x direction is force of friction. So force of friction equals mv squared over r. Alright, so they want us to figure out what this v is. So let's keep going. We've got this force of friction. Remember, force of friction is mu Fn equals mv squared over r. And remember that Fn is just mg, so it's mu mg equals mv squared over r, which is outstanding because now we don't care about the weight of the vehicle. Okay, so it doesn't matter what vehicle it is. So now we've just got mu g equals v squared over r. And then lastly, if they just want v, it's just square root mu gr. And that's it. Alright, so that's one of the easier examples. Let's try another one where it's a little more complicated. So let's make a banked curve. So now we got a slightly different problem here. So now we're going to have a banked curve, which is probably what curves you probably experience when you're on roadways more likely than not. So I'm going to change this though. So your book had this, but I don't know why your book uses beta. Like, let's just use theta like, every other civilized textbook. So so at what angle should we bank this curve such that the car can safely round the curve? Okay, so why bank the curve in the first place? So remember, like the last question, it was flat. So there's some maximum speed you can go. So if you bank this curve, you can go a faster speed. So that's what we're trying to figure out here. So just like always, we're going to draw a Freebody diagram for this. Okay, so there's our curve. So to make matters simple here, let's just keep it frictionless for now. Okay, friction makes it a little more complicated as always. So let's just keep it like this. So we've got a normal force that's perpendicular to the surface, and we've got mg that just pulls straight down. So those are all the forces on here. So just like always, we're going to write a second law equation in our x and y directions. All right, so there's our forces in our x, forces in our y. Net force in x equals ma, net force in y equals ma. Now, this is where it gets a little tricky. So remember when we had things on ramps before and we tilted our axis. But remember why we tilted our axis. We tilted our axis such that the object was going to accelerate along an axis. If this car is going around this bank like this, right, it's accelerating towards the center of the circle. So this means it's accelerating horizontally, which means you do not tilt your axis. So knowing that, let's write our x and y equations. So if, once again, we'll use our y first. Oh, but first we need to identify our theta. Let's go back to our original diagram and see if we can figure this out. So if this is going to be my y-axis, this is my x-axis, right? And my normal force is going to be like so. If they tell me that this is theta here, right? And I know this is 90 degrees apart from here to here, that makes this angle here theta, right? Because if this is theta here, this is 90 minus theta, and this has got to be theta again there. So let's go back here and identify it on here. So that means this angle here is going to be theta. So for our y direction, we're going to have, we got the normal force minus mg equals 0 because it's not accelerating in the y direction. So we got this y portion of this normal force, which is the cosine. So then we'll go to the x direction. Now the only force that provides the centripetal force is this normal force, part of the normal force. So it's going to be Fn sine theta equals mv squared over r. So let's keep on going with this. So let's get rid of this normal force. So I know Fn cosine theta equals mg, which Fn is just going to be mg over cosine theta. And we've seen that before. So let's take this and put this guy right there. This gives me mg, let me do it down here. I've got mg sine theta over cosine theta equals mv squared over r. So great things happen here. Those m's go away. This thing turns into tangent. So I'm going to have g tan theta equals v squared over r. So they want us to solve for theta, so let's just go ahead and finish this up. So theta is just going to be the inverse tan of v squared over gr. And there we go. So you can see that these can get like geometrically tricky, but just like always, draw a good free body diagram, write your equations out, and things usually work out kind of nice. So, all right, so good luck on these next few problems you guys are going to try. Thanks.